So for finding the domain and range, actually it's just the domain, not the range. Find the domain of the function g of x, y, z equals to ln of x plus 2y divided by z. Well, sometimes it might look like it's gonna be like hard to express this domain because we have more than one variable, but in many cases it's a lot easier than it looks. For example, there's a couple of issues with this function. Number one, can z take any value? No. What's the restriction for z? So z cannot be 0. That's it. What about the logarithmic function? Can we input any number to a logarithmic number? What are the restrictions for the logarithmic function?
Greater than 0.
Just greater than 0. So whatever quantity inside of the argument of the function has to be strictly greater than 0. In other words, x plus 2y greater than 0, and in this case you might want to solve this inequality for y, 2y greater than x, negative x rather, and y equal or greater than negative 1/2 x. How do we express the domain in this case? Well, the domain will be not the order pairs design, because this function it's a function of 3 variables. In this case, x, y, and z. So all the order triples such that on the one hand, y is greater than negative 1/2 x, comma, and z cannot be 0. So that's what makes it easy to get this domain, because back when we got like complicated functions of a single variable, we had to put the individual domains and then find the intersection, do the sandwich, and find what were the intervals in common, and that was usually tricky to do. In this case, we'll look at an individual variable and we just list them by variable. That's all we do. It's a lot easier to do. Okay, sketch and graph up to variable functions. So we already did a little bit of this. So let's sketch and describe the graphs of the following. Well, what do we have? F of x, y equals x plus 3y plus z. Well, if we replace f of x, y with a z, that's x plus 3y plus 6. And well, we have all the variables x, y, and z to the first power. So what kind of surface is it going to be? It's going to be a plane, right? So we're going to graph a plane. Let's have all the variables on the left. So that's a negative x plus minus 3y plus z equals to 6. And let's just change the sign to have the first term positive. And of course, we can get the x-intercept, the y-intercept, and the z-intercept. So for the x-intercept, let's make the other two variables, that is y and z, equal to 0. That's going to give us negative 6. For the y-intercept, we make x and z equals to 0 to get the y-intercept. That should give us negative 2. And for the z-intercept, we make x and y equal to 0. That's going to give us z equals to 6. And just a rough sketch. It doesn't have to be perfect. In fact, we have negatives. Those might be a little tricky to graph. So what are we going to have over here? Well, so I will have to extend this to the negative side, and that's going to be, so the x-intercept that goes to negative 6 somewhere here. The y-intercept is going to go somewhere here on the negative side of this horizontal line, and the z-intercept is going to go all the way to 6. So, oh my god, so that's going to be like this, but I'm gonna draw this like dashed to kind of simulate that it's going on the back, you know, on the negative side. Alright, and just shade it real quick, like to make it sort of look solid. Alright, so again, this is a plane. So this is a plane. For the next one, so let's have a look. Number 2, f of x y equals to the square root of 4 plus x squared plus y squared. Well, number 1, let's replace f of x y with z, and that's equal to the square root of 4 plus x squared plus y squared. And well, so let's square both sides to get rid of this radical. And well, so in order to get this to get the graph, which is actually what we're going to do here, it's going to help us understand what we're going to do in the next topic. So, well, I mean, unless you have memorized, remember that table from chapter 1 with the different quartic sections, which I didn't ask you to memorize. You don't have to. In fact, No, you don't have to memorize any of them. I mean, it's not common to just know those from the top of our heads. In the same way that we can identify a parabola, an ellipse, a hyperbola, a circle, you know. So in this case, let's just give z some values. And I'm going to start with, how about z equals to 2. So for z equals to 2, this will be 2 squared. 2 squared equals 4 plus x squared plus y squared. This will be 4 equals to 4 x squared plus y squared. And that's going to be 0 equals x squared plus y squared. Well, the only possible solution to this equation is when x and y are both 0. There's no other way to so in this case, when x equals 0 and y equals to 0, the z value, and I'm going to draw it over here, is going to be 2, right? It's just that order triple. Now for another value, for how about, for example, z equals to 4. For z equals to 4, that's going to be 4 squared equals 4 plus x squared plus y squared. So that's going to be 16 equals to 4 plus x squared plus y squared. Alright, so 16 minus 4, I believe that's going to be a 12 equals to x squared plus y squared. Now, well, if we recognize this equation, what do we have? X squared plus y squared, and the coefficients of both x and y are the same. That has to be a circle. What radius? Well, this number is not a perfect square, but it doesn't matter. What matters is what's the form of this generating curve. And then so what I'm going to go for z equals, let me go a few more. So that's going to be like a circle. And more circles. So this is going to be a circular parabola, which again, these are hard to draw. Let me try my best. I am drawing this. Sort of, right? So it's like a paraboloid, but in this case it's shifted 2 units up. I know it's kind of weird to talk about shiftings in 3 dimensions. Usually we don't do. Usually we get those quartic sections just centered at the origin or with vertices at the origin, but in some cases like this one, this is what we get. All right? So